Hello, this is Dr. Muhammad, and this is Design of Steel Structures according to AISC course. And I'm going to talk about beams, part 3 for today. And the main contents for today's lecture is going to be about three main things, or we can say two main things and then application. The first one is CB. We're going to talk in detail about the CB, the non-uniform bending factor. And number two, I'm going to talk about the bending strength of non-compact shapes. And after that, we are going to take some examples to highlight what we have given or explained. Okay. Now, let's go and understand more about the CB, which is the non-uniform bending factor. So if you recall, last time I was mentioning about, or in the previous video, I said that we have like two cases. If one case that we have a uniform bending, and other case where the beam that we have like gradient bending or non-uniform bending. Okay, and we said that we have different values for CB for each case. We have different values of CB for each case. And we mentioned about this issue, and we said that whenever that we have the uniform bending moment, we are going to have CB to equal to 1, and if it's non-uniform, we're going to have it more than 1. It's going to be 1.3, for example. Today we're going to talk about this in detail, and we are going to understand why this happens. Okay, now let's go to the definition of the CB. Let's go to the definition of the CB and say that, as we have said before, that if the moment within the unbraced length LB, I'm talking about LB here, which means that if we have the compression flanges here, then the distance between the bracing points of the compression flange is going to be LB. Okay. If this moment within the unbraced length is uniform, means that it is constant. So if we have something like this, as I have drawn before, constant, okay, constant value. There is no moment gradient, means that there is no moment gradient. I mean that there is no change in moment across the element, okay. And CB in this case is going to be 1. So in this case, it is going to be 1. CB equals to 1 in this case. Okay, CB is going to be 1. Okay, and we mentioned about that if there is a moment gradient where that the moment is going to be changing along the beam, then we are going to find that this value, the value of the CB, is going to be changed. And it needs to be calculated here. So we have CB here, as you can see. This CB is going to give to us the first, it gives us two different contributions. Okay, the first one is the contribution from the value of the moment. We call it the magnitude of the moment, which is, you can see it in the first fraction here, and I'm going to explain every term in this fraction. Okay, and the second term is Rm, which is going to give us the contribution of the type of the curvature that is going to be experienced by the system or by this element, okay, which is Rm, and we have two cases here. Okay, so let's go first for the CB and understand what this CB is all about. First of all, we are afraid we are going to find that if the element is going to experience a kind of uniform moment, found that every part or every section along the beam is going to experience the same value of the moment, right? So in this case, this would contribute to the resistance or the nominal strength of the structure or the element itself. Okay, and it is going to be related to the values across the member itself. So if we have non-uniform moment like this, we need to know what is the value here, which is quarter length and at middle of the span and 3/4 of the span. So we need to know what are the values here. And this is actually what is given by MA, MB, and MC. So we are going to find that the first part of the CB equation is related to the value or magnitude. It is going to be related to the value of moment magnitude, which is M maximum, MA, and MB, and MC. It is as if it detects the value and the amount of the moment along the beam. And take care that M maximum, it is going to be absolute, and all the moments are going to be substituted in an absolute value. So we are not going to use the value or the sign here. It doesn't matter whether it is maximum or moment. It is positive or negative, I mean. But it is related to whether that this bending moment, okay, how much the values that we are talking about at, as I said, the quarter, okay, MA, and this is MB, and this is here MC, okay. And M maximum, it is the absolute value of the maximum moment within the unbraced length, including the endpoints. This means that if we're talking about singly supported, then M maximum is going to be in the middle. And if we are going to talk about something that the bending moment is going to be changed, like continuous beam, then if we're talking about beam here, then the maximum moment is going to be here. If not, if we have, for example, if we're talking about like element that is something like this, and we have M1 here and M2 here, and we have M1 larger, or M1 is considered to be the maximum moment, then we're going to use it here. This is the maximum moment. Okay, so this is why we mentioned that including end points here. End points are going to be included. Okay. Okay, so this is the first part. This is the first part. Let's go back here, which is this fraction. This fraction. Okay. Then the second part is going to be Rm, which is going to deal with what we call it the curvature of bending. The curvature of bending. Sometimes we have like single curvature, okay, something like this, okay, or something like this, which is, we call it single curvature, okay. The whole element is going to bend in one direction, okay. We call this single curvature. Sometimes we have double curvature, something like this, which means that the whole element is going to experience different type of curvature. We call it double curvature, for example, okay, double curvature. So this part, which is Rm, is going to deal with whether the structure or the beam is going to bend in single curvature or double curvature. Okay, so one part dealing with the value and telling us about the gradient, whether the moment is going to be uniform or not, which is the fraction here. So it deals with the gradient. Okay. However, the second part, or the second Rm, is dealing with the curvature itself. The curvature, whether it is single or double curvature. Okay. This is going to be related to curvature of the bending. Based on that, based on the single or double curvature, and whether there is uniform or gradient moment, we are going, these two values, curvature of bending moment and gradient, both elements are going to contribute in developing CB. Okay, going to contribute in developing CB. So we need to take into consideration both of them. Okay, and CB is representing both elements together. Okay, now let's go to RM again. RM, as we have seen here, it equals to 1 for doubly symmetric cross sections such as wide flanges and singly symmetric shapes such as channels subject to single curvature bending. So it is going to be 1. However, it is going to be calculated by this equation for singly symmetric shapes subject to reverse curvature. Okay, reverse curvature means that we are having like bending moment negative and positive within the same unbraced length. Okay, the question is, what is IYC here? IY, we know it. It is the moment of inertia around the weak axis or around Y. IYC, it is going to be the moment of inertia. This is IYC. It is the moment of inertia of the compression flange, the moment of inertia of the compression flange about y-axis. Okay, so we are talking about the compression flange here. This is what we are going to have, the compression flange. For doubly symmetric shapes, it is going to be IY over 2, because definitely whenever that we are having doubly symmetric, so IY here, this is Y, right? So commonly the cross section or the inertia of the system is going to be around Y. It is going to be due to the inertia of the flanges, not the width. So we say here it equals to IY over 2. For reverse curvature bending of singly symmetric I-shaped sections, IYC is the moment of inertia of the smaller flange. Sometimes we have like single symmetric, we have sections like this, for example, which means that the system itself is like having different cross section for the flanges. Okay, in this case we have small flange and wide flange or big flange. Then IYC should be calculated for the case of the small flange, for the case of the small flange or the smaller flange. All of the beams found in this textbook will be either doubly or singly symmetric. Actually, in our textbook we're going to use doubly or singly symmetric, but this is not the case if you are going to design and you are going to be like an engineer and you're going to find different types of cross sections. Okay, so you need to take care that maybe you need to calculate, and CB need to also to be calculated in a right way. Most will be simply supported. So in the simply supported, we are going to find that simply supported cross section, you're going to find that moment is going to be in the middle, and in the same time you are going to see that it is single curvature, not reverse curvature. So we are going to have CB in general equal to 1. Okay, so that's the point here. When the bending moment is uniform, the value of CB is going to be 1, right? Because M is going to be used in the numerator and denominator. So the fraction output results in 1. Okay, and also we are going to find that RM also has been taken as 1 because it is written here. It's supposed to be here. So whenever that we are going to use simply supported case where the gradient is not going to be there, then we are going to take the CB equal to 1 and RM is going to be 1. Otherwise, you need to calculate, as we have explained before, you need to calculate CB based on the 2 parts that we have mentioned, and we have mentioned also what is the rationale behind every part of them. Okay, now the question is, what do we need from this? Why CB that we are like it is, why it is important for us? Okay, so maybe we're going to see this in the next slide. If you remember, I was talking before about the nominal flexure strength for compact section. You're going to find this slide on in the previous video. If you look to the summary, of the flexure strengths for compact sections, you're going to find that we have different cases. We have the case where that, do you remember this? Here and here. This is here, it is going to be LP. Here, this is LR. And we said that this part, it is the inelastic lateral torsional buckling, and this part is going to be the elastic. So ELTB means that elastic lateral torsional buckling. Here, it is inelastic ILTB. Okay, we mentioned about this last time. And you are going to find that whether it is elastic or inelastic lateral torsional buckling, where that our unbraced length is going to be between LP and LR, or going to be larger than LR, here LB between LP and LR, which here this is for the inelastic buckling, lateral torsional buckling, and here it is the case of elastic torsional buckling. You are going to find CB is going to take part in the nominal strength calculation. Nominal flexure strength is going to be contributed. This means that CB, for example, if we found CB equals to 1.67 for some specific cases, for example, this means that we are going to increase the nominal flexure strength of the beam by 67%. So it is quite a number to be included whenever that we are calculating the resistance or the nominal flexure strength. So for LTB, whether it is inelastic or elastic, CB is very important to be calculated, because we are going to increase the resistance of the system or the structure or the element itself by putting this CB more than 1. It is going to be larger than 1 in our case. But for the case where that we are dealing with plastic moment, where that no lateral torsional buckling issues, then where that LB is less than LP, then the nominal strength, nominal flexure strength is going to equal what? The plastic moment. So actually CB has nothing to do here. Okay, it has no role here. Okay, it's going to be in plastic. And this is what I put it here in this note. CB is important in case of lateral torsional buckling, whether it is elastic or inelastic. Okay, but not included in the case of LB larger, smaller than or equal to LP. This case where that the plastic moment is going to be used, where that the first part, if we say that this is like part 1, this is 2, and this is 3, we are talking about part 1 here, zone 1, which is the plastic part. CB does not contribute. Okay, whether the system is going to have single curvature or double curvature, whether there is gradient of moment or not, it does not affect the flexural or nominal flexure strength of the element in this case. Okay, this is only an important note I'd like to highlight for you. Okay, now let's go to another part that it is important. I think it is important to be highlighted, which is why we need to understand what is the main reason for this, especially whenever that we are talking about like uniform and non-uniform moments. We mentioned before that they are going to contribute, okay, to the nominal strength of the section. So what is the reason for this? Why in case of the uniform we say that CB, for example, is going to be 1, or in the case of non-uniform we found that CB is going to be like 1.3 or maybe more or something. So why the change in moment is going to make this this importance for us. Okay, this is actually a part from Salmon and Jensen book, 5th edition. I just like copy and paste here, and I'm going to discuss with you and like explain and discuss together. So they put it like this: when the bending moment acts with a gradient having maximum moment at one end to 1/2 that amount at the other end, the residual stress effect is relatively insignificant. Okay, residual stress effect. Do you know what is the residual stress effect? I'm going to show it to you in a minute. Okay, but remember that this residual stress is going to have relative little significant rule. Okay, little rule, or not important, relatively insignificant rule if we have the gradient, okay, moment. In this case, only a small portion of the span near maximum moment will be inelastic. Okay, in this case, only the near the maximum, okay, in this case, only a small portion of the span near maximum moment, where here, for example, will be inelastic. Okay, so this means that we are going to, the gradient of moment is going to make the role of residual stress, okay, going to be insignificant. Okay, because why? What is the reason for this? Okay, in this case, only the small portion of the span near the maximum moment here, this part, which is the span near the maximum moment, will be inelastic. It will experience the inelasticity here. But when the load, and then when the load, or when the applied load stress is lower, okay, the addition of residual stress will be less likely to cause a fiber to reach yield stress. Okay, so this means that we have part that is going to reach yield, okay, and if, or when the applied load stress is lower, the addition of residual stress will be less likely to cause a fiber reach yield stress. Okay, so this is the rationale behind the moment gradient, why that we are taking CB higher. CB higher than 1 means that we are increasing the resistance, the nominal flexure strength, right? So let's go and understand how this would like give difference. For example, here we have, this is the relation between LB and M here in the vertical axis. So as you can see, this is M nominal strength, and this is the unbrazed length. And this is the common three different parts that we have. We have the plastic part, we have inelastic lateral torsional buckling, and we have elastic lateral torsion buckling. Okay. And then for one section, which is W16 by 26, for example, we are going to find that for two different cases, one case where that the moment is having gradient along the beam, this CB is going to be 1.3. Look how much that compared to the case where that the moment is going to be constant. So here we have gradient, okay, gradient moment. Over here it is going to be uniform, okay, uniform. Then you're going to find that in this case CB equals to 1. The meaning is in region or zone 2 and zone 3, inelastic and elastic lateral torsional buckling, you're going to find that for the case of the gradient moment, the strength, the nominal strength is going to be higher, okay, as you can see by this amount, almost like CB is going to be here 1.3, almost like 30%, for example, if we're talking about something here. I mean that this is how you should look to the two cases, that you are going to have extra resistance here, okay, compared to the case of the uniform moment. Both of them, they are having the same cross section, which is W16 by 26. Okay, so this is considered to be the beam behavior of this section as related to lateral support. Okay, and this is from some research books. It is from Ura and Galambos, okay, and Rivendra. Okay, this is in textbook. Actually, I also, this is copy paste from Selman and Jensen, and you can find this figure in 9.5.1, and I hope that you can like revisit this part, because it's really important and it's given, or it's discussed there in more details. Okay, as I said before, the textbook that we are using, which is SIGWI, it is good in general for the student level, but if you want to go into or to understand in-depth knowledge, then I strongly recommend other references like Salmon and Jensen, for example. Okay. Now I want you to understand what is the meaning of residual stress that we have mentioned before. So I'd like to recap what I have mentioned before. The point is we are talking about CB, and this CB, it is having contribution from two different parts. And after that, we mentioned that why it is important to know about CB. We found that it has some role in lateral torsional buckling zones, whether elastic or inelastic, and we are going to consider it, and it is going to increase our nominal flexure strength. And when we go through the main reason for having the gradient or the gradient moment to give us higher resistance, as we said here, as we have mentioned here, we found that we are attributing everything to what we call it residual stress effect. So we need to understand what is this residual stress effect, how we can, what is this kind of stress that is going to make the gradient moment to have a great contribution for the resistance of the structure. Okay, so this is what we want to know. So from here we need to understand what is the residual stress. So residual stresses are stresses that remain in a member after it has been formed into a finished product. This is the definition of residual stresses. It seems that during the manufacturing process, you are going to find that there are some residual stresses going to be there. Such stresses result from plastic deformations, which in structural steel may result from several sources. So the main cause is, the root cause is plastic deformation. So why this kind of plastic deformation are going to take place? Because of several sources. Number one, due to uneven cooling, which occurs after hot rolling of structural shapes. Or number two, cold bending or cambering during fabrication. And number three, punching of holes and cutting operations during fabrication. And number four is welding. Okay, so under ordinary conditions, those residual stresses resulting from uneven cooling and welding are the most important. So the first one is the most important one. Actually, the important residual stresses due to welding are really the result of uneven cooling, which is number one and number four. They are like related to one another. If you look to this figure, and still we are taking it from Salmon and Jensen, you're going to find that this is the cross section that we have, the I shape, and you're going to find this is the maximum compressive stresses, say 12 KSI average, which is 83 megapascal, which is something significant actually if you are going to like put it, if you are going to take it into consideration. Okay, to some extent, of course, it's not very big, but anyway, it is going to like increase, and this effect, as we said, going to be like augmented if we have the like uniform moment. Okay, in this case we are going to find that in case, as I said, in the non-uniform moment, the part where that is near the maximum is going to have the inelastic or going to yield, the parts where that is going to experience yielding here, but other parts it is less. The contribution of residual stresses here is much higher than here. Okay, so that's what we were talking about, and this is the compressive stresses due to residual stresses. Here this is the maximum negative or compressive, and negative stresses here. Okay, now this is the influence of residual stress and stress strain curve in general, to know how that it will affect our stress strain curve. If we have a stress strain curve, which is the average compressive strain here, and here we are going to have the average stress, which is, let's assume it is the average stress here, which is P over area gross of the cross-section. So the solid line is giving us members with residual stress, which is the actual, okay, the actual stress strain curve. But the dotted line is going to give us, as you can see here, the dotted line, it gives us the ideal coupon containing no residual stress, whereas it is, as you can see here, this is F field, and actually this F field theoretically should be like this. Okay, so this is what we call it, the maximum residual compressive stress that is going to be added to the system. So in point 1 here, it is the start of the slope to be changing. You're going to find at point 1 the edges of the flanges. Okay, the shaded portions indicate portions indicate areas which has achieved stress F field. So here F field achieved already, which is at the edges of the element. And at point 2, we're going to find here, this is point 2, we're going to find that the portions at the edges of the flange are increasing, and something in the middle of the web is going to start to propagate or start to develop. And then at point 3, you're going to find that the whole shape is going to be under yield stress. Okay, so here we can find the difference between section with and without residual stresses. Okay, now we are going to talk about one example, including with the inclusion of CB for non-uniform bending factor. We're going to consider it, and we are going to look how much it is going to contribute to our results. Okay. Now let's have an example. This example is 5.5. You can find it in the textbook as well. So determine CB. Now it is clearly that we are asking or searching for CB for a uniformly loaded, simply supported wide flange with lateral support at its ends. So we are having like simply supported as you can see here, here and here, and we have like a distributed load, okay, uniform distributed load, and it is simply supported. Okay. Now because of symmetry, the maximum moment is at mid-span, because we know that maximum moment is going to be in the mid-span here. So this means that M maximum, okay, which is going to be needed for our CB calculation. So M maximum equal to MB, okay, because MA, if you remember that we have here MA, and here it is MB, and 3/4 it is MC, right? So MB equal to M maximum, right? So we are going to have M maximum equal to MB. So based on that, we know M maximum and MB. It is going to be WL squared over 8, where L, it is the total length of the flexural or this beam. Also, because of symmetry, the moment at the quarter point equals the moment at the 3/4 point. So MA equal to MC, right? So here, this is point A, and this is point C. They are going to be the same because of symmetry. We have acts of symmetry here. So this MA equal to MC, and it equals to WL over 2 times L over 4. This is the reaction here. We're going to take the moment here. So the reaction here is going to be WL over 2 times WL over 2 times L over 4, which is the distance between the support and the point A, and this point A, minus the contribution from the uniform load, which is this part, the reaction heading up and the uniform load is heading down. So we are going to have WL over 4, which is the force here, WL over 4, times this distance, which is going to be L over 8, which is this distance here, L over 8. So after calculation, we're going to find that MA equal to MC equal to L over 32 times WL raised to the power 2. Now we have M maximum MB, we have M maximum, we have MB, we have MA and MMC. So everything is okay for calculating CB. Okay, calculating CB. Let's go and calculate CB here. Okay, since this is a wide flange shape, which means that doubly symmetric and is simply supported with gravity loading, this means that it is going, if we have the supports here, okay, this means that we are going to find that it is going to have a single curvature, right? It's going to have single curvature. Means what? RM would equal to 1, single curvature, because it is single curvature bending. So RM is going to be 1. From AISC equation F1-1, chapter F, okay, then we're going to put CB equal to the equation that is long times RM here. But as we said, this RM equals to 1. This RM equals to 1. Okay, now after substitution here in this equation with everything, M maximum here and MA and MB and MC here and here and here, then we're going to find that our CB equal to 1.14. 1.14. What is the meaning of this? This means that for this wide flange shape, which is a doubly symmetric shape, and it is going to have single curvature bending for simply supported beam, the strength for lateral torsional buckling, whether it is elastic or inelastic, is going to be increased by 14%. That's the meaning of CB here. This means that the shape can resist 14% more compared to the uniformly moment case along the beam. If we have another case where that the beam that is going to have uniform bending moment, okay, with the same cross section, with the same everything, okay, RM is going to be 1 also, but the fraction here is going to change. So we're going to find that it is going to be 1. CB equals to 1 in this case. CB is going to equal to 1. So this is what I want you to understand, that CB can increase the nominal flexure strength by 14%. I'm going to share with you different shapes where that you are going to find that the shapes can increase, or the nominal flexure strength can reach like 60% and 70%. Okay? Okay. Look here, this is for different cases. CB for several common cases of loading and lateral support. Values of CB for other cases can be found in part 3 of the manual, Design of Flexural Members. You can find it there. Now, as we said, that the crossing here means that the compression flange is braced. So really, LB is going to be L here. The unbraced length is going to be the total length between the support. In this case, which is the case that we have, we've just solved, okay, in the previous slide, we found that CB equal to 1.14, right? Because the same condition as the example that we've been discussing. And if we have the same, the same cross section, for example, but we have another point of bracing in the middle, so LB is going to be half of the length, then we're going to find that CB is going to be increased by, or going to have 1.3. This means that 30% increase, okay, almost 30% increase. And then if we are going to have moment concentrated at the ends, M1, and this is M2, which is the same value, and LB equal to L, you're going to find CB equal to how much? 2.27. Very huge here. Okay, very huge. Means that almost double, more than double. The nominal strength is going to be doubled here. Similar here for AB and CD. CB is going to be for this part, which is part AB, this part, and CD, AB and CD. CB is going to be 1.67. However, for BC, it is going to be 1 in the middle. Okay. And similar for this case, CB 1.32, concentrated load in the middle. Here, concentrated load in the middle, but we have support. It is going to be 1.67. And then concentrated moment at one support is going to be 1.67. Okay, so these are the main differences. For unbrazed cantilever beams, so if you are talking about cantilever beams, then AISC specifies a value of CB equal to 1. So for unbrazed cantilever, if we have a cantilever like this, so CB would equal to 1. This is according to AISC. A value of 1 is always conservative, means that even that you are having different cases here, but always the least value is 1, right? This is the conservative value that we can use. A value of 1 is always conservative regardless of beam configuration or loading. So whether that's taking into consideration the configuration or loading, so CB can be taken as 1. But in some cases, it may be excessively conservative. This is my concern here. That if you are not going to take it into consideration, like this part, this case for example, look here, CB is 1.67, or maybe this case where that it is going to be more than double, 2.27. Okay, if we are going to see here, for example, the strength, or that what we were discussing, CB is directly multiplied by the value of the fraction here. So 1.3 means that 30% increase. Similar here also, FCR, it is going to be multiplied directly by S6. It's related directly to the nominal flexure strength. So increase by 1.67 means that really huge increase, Okay. Okay, so we need to take into consideration this is the most common types of cross sections and loading condition and configuration as well that is commonly going to be encountered. So we need to take into consideration what the CB value. Okay, this is a small to show to you how much the difference is going to be. If we have LP, LR, and L bracing, for example, if it's the unbraced lenses here, for example, then are going to find that, look here, this is CB equal to 2.3, this is CB equal to 1.3, here CB equal to 1. Okay, so if we have something, if we have an element here, for example, so you can find the difference here. As I said, it's huge. It is going to be huge difference. Okay, so economically, you need to take into consideration CB. Okay. Now let's go to the next part, which is related to the strength, bending strengths of non-compact shapes. We are going to calculate the bending strength for non-compact shapes. Okay, so bending strengths of non-compact shapes. Okay. Bending strengths of non-compact shapes, if we're going to deal with specific shapes like wide flanges and miscellaneous standard shapes and channel, okay, C shapes, are compact. Commonly, most of them, they are compact. Most of these shapes, they are compact. Wide flange, M, S, and C, they are compact. A few are non-compact because of the flange width thickness ratio. So few of them is going to be non-compact because of the flange, not because anything else. In general, let's go and examine what are the failure modes of our non-compact shapes. In general, a non-compact beam may fail by 1, 2, 3. It is similar to the compact shapes as we have mentioned before. Whether it is lateral torsional buckling, elastic or inelastic, flange local buckling, elastic or inelastic, or web local buckling, elastic or inelastic. Okay? So any of these types of failures or failure can be in either the elastic range or inelastic range, as I said. The strength corresponding to each of these three limit states must be computed, and the smallest value will control. This means that you need to check all of them and then see which one is the least, and it is going to be the governing condition. Fortunately, we're going to find that the web of most of the shapes, or most of the shapes, hot rolled shapes at least, they are compact. This means that you need not to check condition number 3, web local buckling. Okay, only you need to check the first two. Okay, so here the whips of all hot rolled shapes, take care, we're talking about hot rolled shapes, in the manual are compact. So do not worry about the web local buckling here, they are compact. So the non-compact shapes are subject only to the limit states of lateral torsional buckling or flange local buckling, which is the first condition or first failure mode or the second failure mode only. Okay. If we have built up welded shapes, okay, however, can have non-compact or even slender whips, as well as non-compact or slender flanges, because it is built up. They are built up shapes, so we are not sure, or we might not. We need to check, okay, the flanges and the whip, whether they are going to be compact or not, non-compact or slender. These cases are covered in AISC section F4 and F5. Okay, F4 and F5 under chapter F. Built-up shapes, including plate girders, are covered in chapter 10 on the textbook. Okay, you're going to find it, but we are not going to use it, or we are not going to explain it under flexure member. They are going to be explained separately. Okay. Okay. If the shape is non-compact because of the flange, the nominal strengths will be the smaller of the strengths corresponding to flange local buckling and lateral torsional buckling, as we said. So now we're talking about the flexural strength, okay? Because we're talking about flange only here, because whips are compact for hot rolled sections. So we have two cases, okay? So this is for non-compact, as I said, non-compact. Okay. Flange local buckling or lateral torsional buckling, right? So in the flange local buckling, if we are worried about it, we need to check what we call it lambda. So lambda equals to B flange over 2T F, 2T flange, right? And if it is less than lambda P, what is lambda P? It is the plastic limit, which is 0.38, the radical of E over F field, right? So there is no flange local buckling in this case. Do not worry about it. You have the slenderness of your section is very, okay, is going to exceed this, is going to be less than the limit. This means that we're talking about the flanges, remember? So this means that we are on the safe side. No flange local buckling. Do not worry about it. There is no local buckling for this. Okay. But if our lambda is larger than, which is going to be here between LP and LR, then we should worry. The flange is non-compact, and in this case we are going to obtain the nominal strength. Okay, the nominal strength is going to be nominal flexure strength, of course, equals to M plastic minus 0.7 F yield SX. Okay, so this times lambda minus lambda P over lambda R minus lambda P, as we have explained before. So case there is no flange local buckling, do not worry about it. And the case where that we should worry about the local buckling, or we are going to say that it is non-compact and the nominal flexure strength should be calculated like this. Okay, the last case is lambda larger than LR, which is slender, and we are not going to cover slender here. Okay, slender is going to be covered later. Okay, slender sections. Okay, so this is the first case, which is flange local buckling. Let's go to the second case, which is lateral torsional buckling. Lateral torsional buckling. Using LP equal to 1.7 R, 1.76 RY times the radical of E over F yield. So we have like three cases, right? First, if LB, less than LP. So there is no lateral torsional buckling here. This means that we are in zone 1, plastic part, this part. Do you remember? So the brazed length is less than or equal to the plastic limit. So we are here. So no lateral torsional buckling. We should not worry about this. Okay. And case number 2, where that LB is between LP and LR. So this means that we are in the we are in the inelastic lateral torsional buckling here. This is the area that we want to. We are here. Okay. And if not, okay, so in this case, the nominal flexure strength is going to be, yes, CBE is going to be here. Similar. So CB is going to contribute here. MP minus 0.7 F yield SX and LB minus LP over LR minus LP. And it should always, of course, less than the plastic moment. We should not exceed the plastic limit. The other case is if we are here in this area, which is the elastic lateral torsional buckling. In this case, LB larger than LR. So we are here, right? There is elastic lateral torsional buckling, and the nominal strength is going to be FCR times SX, and in all cases they should be less than the plastic moment. FCR is going to be also the contribution of CB is here, and then pi squared E over LB RTS, and then this fantastic radical here. Everything that is written in this under this radical already we have explained it in detail in the previous video, so please revisit it. It is only fixed values that we can, or at least it is fixed definitions there, and you can understand them well. Okay. Okay, now let's go to the next, which is we need to have an example to follow or to explain what we have done up till now. Okay. In our example, a simply supported beam with a span length of 45 feet is laterally supported at its ends and is subjected to the following service loads. So we have service loads here. We have dead load and live load. 400 dead load, and the live load is 1,000 pound per foot, including the weight of the beam. Okay, so we have dead load and we have live load. F yield is 50 ksi, and the cross section is going to be white flange 14 by 90. Okay, we want to check whether this section is adequate or not. We want to check this section is adequate or not. Okay, so first, the first and the foremost important thing that we need to check in the beginning is what is the type of the shape. Okay, so determine the shape type, whether it is compact, non-compact, or slender, right? So how we can obtain this? We are going to check first lambda for it. Lambda for this cross section. Okay, first of all, we know lambda if we're talking about the flange. Okay, now let's understand where we are. Okay, we want to know what is the shape. It is compact, non-compact, or slender. Because if it's compact, then we need to go to the previous lecture, previous video. If it's non-compact, then we're going to deal with what we have learned in today's video. Now let's go and get first P flange over 2TF. We're going to find it 10.2. From where? Go to the dimension and properties table for this cross section and obtain BF and TF and check this value. So I am strongly recommending for you, or I strongly recommend for you, stop the video now and grab your manual and try to check the values of BF and TF. Okay, so this is lambda, slenderness ratio. We're talking about the flange here. We're talking about the flange. Then we need to know the limits for us. Lambda P, plastic limit, lambda R, slenderness limit, okay, or proportional limit. So here we are going to have 0.38, the radical of E over F field. This gives us 9.15. Remember that E for steel constant, it is 20,000 KSI. F field is given already for us here. Okay, and lambda R, it is going to be 1 times the radical of 29,000 over 50 KSI. This gives us 24. So this means that we have lambda P here, we have lambda R here. Lambda P found to be 9.15, lambda R it is 24.1, and we are here, which is 10 point something, 10.2. This means that we are between lambda P and lambda R. Okay, so we are here. So this means that our flange is going to be non-compact, right? Non-compact. This means that our section is going to be non-compact as well. You might ask me that we didn't check the flange, we didn't check the web here, web, we didn't check it. Yes, because it is hot rolled section, and web for all hot rolled section is going to be compact always. So no need for us to check for the web. It's enough for us to check for the flange. If the flange is going to be non-compact, this means that the whole shape is going to be non-compact. So our shape is flanges are non-compact, however the web is compact. This means that since our lambda is larger than lambda P and less than lambda R, this shape is non-compact. This shape is non-compact. Check the capacity based on the limit state of flange local buckling. Flange local buckling. We are going, this is in the next slide. Flange local buckling is going to be used in order to check the capacity of our section. Okay, so we are going to check two things as we have mentioned before. Okay, first we need to check the flange local buckling, and then we're going to check after that lateral torsional buckling. Totally different than one another. Okay, flange local buckling and then lateral torsional buckling. What is the capacity of them? So first of all, for flange local buckling, flange local. Let me check something here. Quiet, okay, it doesn't work. So flange local buckling, it is going to give us some capacities. Okay, and then we are capacity. Let's assume 50, anything, for example, and here lateral torsional buckling is going to give us another capacity, which is, for example, 60. This means that we need to check both, and then we're going to follow the one that is giving to us the less, which is flange local buckling, for example, here. This is our strategy. This is how we are going to use it. Okay? Okay, so if we go back here, we're going to check this part is flange local buckling. And from here, we are going to check like lateral torsional buckling. And we're going to see what is the difference between the two. Okay, so now for the first part, we need, according to what we have said here, it is non-compact section, right? If I go back, okay, and we said that for flange local buckling, we need to check lambda. We need to obtain lambda P and lambda R first. Our case is here. So this means that it is non-compact. Then this means the nominal flexure strength is going to be M plastic. This means I need to calculate M plastic minus what we can see here. Lambda P, lambda R, lambda P. Already we have explained it. F field is 50 in our case. Sx, we need to check it or get it from the properties table. Okay, so and this is actually what we are doing here. So we need to calculate M P. First, the plastic moment. This is going to be F field 50, we know it, ZX, because our cross section, as I said, okay, we're talking about X, okay, so we need to obtain ZX. From where? Go to the table, stop the video, go to your manual and check the table. You're going to find this value, 157. This is MP. Then, because we are non-compact shape, our nominal flexure strength is going to be less than M plastic. Okay, it is going to be M plastic, which is already calculated here, 700 or 7,850, minus something M plastic again, minus 0.7 F field times SX. Again, this is from the table. ZX and SX, this is from the table. Times lambda minus lambda P over lambda R minus lambda P. You can calculate this, and you are going to find that this is the value here. What is the meaning of this? This is the capacity based on flange, okay, local buckling. This means that if the stresses or the nominal flexure strength of this section is going to resist this amount, which is 7,650 inch kips moment, after it, flange local buckling would happen. So if we have the flange here, okay, then flange local buckling is going to happen. Okay. So now this is FLB, first case. Okay. Now let's go to the second case, which is lateral torsional buckling. Let's check whether that the cross section is going to have lateral torsional buckling or not. Do you remember what is lateral torsional buckling? As I said, that the system is going to have something like this. Go laterally and torsional. This is global failure phenomenon. This is local failure phenomenon. Okay, we do not know which one is going to happen for us. Okay, at least we know now this is the capacity based on flange local buckling. Let's go now and check the capacity based on the limit state of lateral torsional buckling. Lateral torsional buckling, LTB. We are going to use another technique this time. We're going to use ZX table. What is the meaning of ZX table? ZX table, they are going to provide for us LP and LR for the section that we are searching for or that we are examining. Okay, so now stop the video and go and bring your manual and check ZX table. It is going to be providing for you LP and LR. Okay, from where we can get this this ZX table, okay, then we are going to show you in the next video, in the next slide here. So go to the manual, table 3-2, okay, continued means that it's not the first page in this table, okay, for wide flange shapes under F field equal to 50 KSI, and this is selection based on ZX as it is given here. You're going to find on the left ZX or ZX with big letter here. Look to the table and you're going to find here in the most left column here, in the first column here, it is giving to us the shape. So check the shapes here. You are going to find one of them at the middle here. This is wide flange 14 by 90. Here, wide flange 14 by 90. Okay. Okay. And then you are going to look across the table. You are going to find LP and LR are given for us. LP and LR. Do you remember LP and LR? They are so long equations to calculate. So if you could know how to get it from the ZX table, then it would save you a lot of time. For LP, you're going to find it 15.2, and for LR, you're going to find it 20 or 42.6. Okay, this is LP and LR. So the table is giving to you, the left column gives you shape, ZX after that, and then different values for the LRFD and ASD moments. Okay, and then you are going to find these columns here, LP and LR, are going to be given. Remember, they are being provided by as in foot. Okay, so if you are using another set of units, you need to take into consideration the conversion between the imperial units to your units. Okay, so this is what we are going to use now. LP for us equal to 15.2 and LR equal to 42.6. Easy to be obtained. Right, let's go back here. So we have LP 15.2, LR 42.6. If you remember the equation of LP and LR, it was very long, right? So if we do not like to go through it, I think that we have explained it before. It's not here. I think it's in the previous slide or previous video, I guess. So anyway, you know that it's very long and you need to calculate it. It will take longer time for you. But if you could find this table 3-2, you're going to find, or you're going to save a lot of time for you. Okay, it's going to save you time. Okay. Now we have now LP and LR known for us. Our unbrazed length is 45. I think it's given from the beginning, 45 feet. Okay. Then our failure, it seems that 45 is between 15 and 42. Sorry, it's larger. Larger than LR. So if we have like LP here, we have LR here, and these are the limits, okay, for us. So here it is 15.2, here it is 42.6. Our case, we are here, right? So this is LB, the unbrazed length, which is 45. This means that we are in the inelastic, elastic part. So if we have something like this, okay, so we are here, this is LR, right? And we are here, which is LB. So we are in the elastic part, zone 3, okay, inelastic buckling. Okay. So now from part 1 of the manual, you are going to find that IY, which is the least moment of inertia, RTS 4.11, H node J CW, they are given from part 1 of the manual. Please stop the video, go to the manual, check these values now. Okay, it's important to get familiar to the manual. It is important to get familiar to the manual. Please check all of these values from your manual. For a uniformly loaded, simply supported beam with lateral support at the end, so it is lateral support here, means that we have crossing here, and another crossing here means that unbrazed length, this is LB, and it is uniformly loaded, means that we have uniform loading, okay, at the ends. This means that our CB equal to 1.4. From where I got this 1.4? It is from the figure that we have explained before. And if we go back, do you remember when I was talking about the figures? Yes, this is here. This is our case. Okay, from where I can get it from the manual? You can get it from part 3 of the manual, design of flexural members. You can find it there. Okay, so we have like simply supported, braced, take care, braced at the supports, because maybe we can have another bracing in the middle. So CB is going to be totally different than CB here. Okay, so our case is CB equal to 1.14, uniformly distributed load, simply supported at the ends and braced at the ends. Okay. Okay, now we have CB equal to 1.14. Okay, for doubly symmetric I shape, C equal to 1 according to AISC equation F2-4, okay, gives this value FCR. Okay, FCR. You are going to find all the values that all the All these values are going to be used, including this C here. So we're going to find it here. CB, we have 1.14 pi squared E LB, which is 45, RTS given to us 4.11, 12. It is the conversion. Take care of the conversion. Okay, if we are going to converge from foot to inch, because our final result, it is in kilopounds per square inch. So take care that our 45 feet, it is in feet, so we need to convert. Then E, and the radical, after that everything is known for us. This is C, it is 1 as we said. J, already we have obtained it. SX, H node, LB and RTS, everything is okay. Then we obtained that to be 37.2. From ASIC equation F2-3, we're going to find the nominal strength is going to equal FCR times SX. Okay, let's go back again because we are lateral torsional buckling. Do you remember? We are in lateral torsional buckling part. So we check our lambda and we found that we are in case number 3. LB larger than LR. So our nominal flexure strength is going to equal FCR times SX, and it should be less than MP, and it should be less than MP. Based on that, we have calculated FCR, and we found that after the obtaining all the values inside this fantastic equation, we ended up with, yes, this is FCR, and this is what we have obtained, 37.2 KSI. Then from the equation that we have indicated before, FCR, which is 37.2 times SX, from the table, okay, we can obtain this value. What is this? The nominal flexure strength for elastic lateral torsional buckling for the cross section that we are examining now. It is 5,320 inch kips, and we should check the last check for us that it should be less than MP. Already we have explained that before. That is MP. M plastic, it is 7,850, and our case it is 5,000 something, so definitely it is less than MP. Okay, so we are based on elastic lateral torsional buckling. As I said many times, we are here. Okay, we are here, elastic lateral torsional buckling. Okay, so now let's check for lateral torsional buckling. For lateral torsional buckling, the capacity is 5,003 inch kips. It is inch kips here. And for flange local buckling, let's go back and see. Flange local buckling, it was 650. Okay, so this means that we are having, okay, it has been like erased here. So anyway, so for flange local buckling, it is 7,660. Okay, and for the elastic lateral torsional buckling, it is 5,300 something. Here it is 7,000, here it is 5,000. So based on this, so lateral torsional buckling is controlling. This value is going to be controlled. What is the meaning of that? Lateral torsional buckling means that our cross section is going to fail first, okay, by lateral torsional buckling. It is going to like fail in this way. This means that lateral torsional buckling is going to take place before flange local buckling in our case for this cross section. Okay, and based on this, we are going to say that for LRFD, our design strength means that for LRFD, we are going to use the resistance factor to be used. So the nominal strength, which is the 500 or 5,320 inch kips, is going to be multiplied by 0.9. Okay, and we are going to obtain the value for this nominal, not nominal now, it is the design strength. Design strengths that we should use for comparison with the required strengths based on loading. So this means that we are having almost 400 foot kips. The factored load and moments are our factored load. Remember that everything were given to us. We have dead load, we have live load, 400 and 1000, right? So we are going to calculate the values for the maximum moment coming from this required load. Commonly, as I said many times, the gravity loading, okay, gravity loading, which is 1.2 dead plus 1.6 live, is going to control as long as we do not have wind or we do not have seismic. Okay, so 1.2 times 0.4, which is the 400 of the dead load, plus 1.6 times 1, which is the 1000 of live load, it gives us this distributed load to almost 2 kips per foot, and M ultimate, because we are having, as we said, we are having simply supported, so the moment is going to be WL squared over 8, which is WL squared over 8. This is the required moment, which is 527. Okay, so this means that our required moment requires 527. However, the capacity based on lateral torsional buckling of our cross section, it was almost 399. Okay, so the required is larger than the capacity. This means that our system, our cross section is what? Is not enough. This section is not enough. We need to increase the cross section. Okay, so we need to increase the cross section. And this is what we have said here. Since M ultimate, the required moment, is larger than phi b Mn, which is the design strength, the beam does not have adequate moment strength. Does not have adequate moment strength. Remember that in the equation we want to know whether this cross section is having adequate nominal or adequate strength or not, flexural strength or not. The answer is no. The answer is no. If I say to you, what is the mode failure that is going to take place here? It is going to be elastic lateral torsional buckling. It will not resist elastic lateral torsional buckling. Okay, and the capacity is going to be exceeded here. Okay. Okay, I hope that we have understood this well, and I hope that based on what we have explained, we can understand well how this example is going to work for us. Based on these loads, our section is going to be vulnerable, okay, toward elastic lateral torsional buckling, and the cross section needs to be changed. Okay, and flange local buckling found to be, there is no local buckling for the flange would happen. So if we are going to look at the end, let me check this. Okay, it doesn't work. Okay, so if we have, this is the cross section that we have. Okay, at the end now. So we have different parts. First we have the flange, 2 flanges, and we have the second part in the whip, and the third part, which is the total cross section, all of it. So we found by analysis that the total cross section, first, the whip is not going to work is not vulnerable to any mode failure because it is exactly compact. We do not worry. We're not going to worry about it. When we checked the flange, we found that it is non-compact. Non-compact. So we should be worried about it. We need to get what is Mn, what is the nominal strength for it. And we check after that the total system, or the total cross section, the whole cross section against lateral torsional buckling. So we need to check lateral torsional buckling, nominal strength as well. Okay, so we checked both of them. We found that this lateral torsional buckling elastic one is going to be the controlling one. When we compared it with the given loads, we found that it is less than the required flexural strength. This means that it is not going to work for us. Okay, I hope you understood, and I hope that everything is clear for for you. Please try to read the material again, try to go through the video again and listen to it again. Try to understand. By the end of this lecture, you need to understand what is the difference between the flange local buckling and web local buckling and lateral torsional buckling. And we said that for each one of them we have elastic and inelastic. Fortunately, for our case, for hot rolled section, we found that web local buckling is not going to work for us. It is always, in our case, it is compact. Always it is compact for hot rolled sections. Then we need to check always the flange local buckling or lateral torsional buckling. This is what we need to check every time. This is what we need to check every time. So by checking, we found that sometimes local failure mode would happen if FLB would occur, or global, which means that the whole section, if it is lateral torsional buckling, whether it is, as we said, whether it is elastic or inelastic, and here it is elastic or inelastic. Okay, this is the summary of what I have explained today. I hope that you understand it well. Thank you for listening, and see you in the next video.